Welcome back to Calculus 1. Today we're going to talk about infinite limits. I want to begin by looking at the function f of x equals 1 over x. The graph is simple enough. As x gets big, it goes to 0. As x goes to 0 from the right, you'll have 1 over very, very tiny little numbers. And as you know, if you divide by tiny numbers, you get huge numbers. Fundamental principle of mathematics is 1 over tiny is huge. Also, 1 over huge is tiny. We're seeing both of those here in the graph. If you plug in very tiny positive numbers, the function grows bigger and bigger and bigger. And as you plug in numbers that are bigger and bigger, you get numbers that are smaller and smaller and smaller output. You get kind of a symmetry here through the origin for negative values. 1 over a negative is still negative. So you end up in the third quadrant over here. What would you say if we had to investigate the limit as x goes to 0 from the right of 1 over x? Doesn't this function blow up and go to plus infinity? What does that even mean? Let's see how we would define the limit as x goes to a. What do we mean by the limit as x goes to a of f of x equals plus infinity? If you choose some number m, there will be some level of closeness, some delta in the domain, so that if you stay within that delta, the function values will rise above whatever m you choose. That's the definition. Given some m greater than 0, no matter how big, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus a is less than delta, then the function value is greater than m. It will be above this level of bigness that you chose. So what do we mean by function going to minus infinity? The limit as x goes to a of f of x equals minus infinity means, given m less than 0, some cutoff way down here, there exists some delta greater than 0 in the domain, so that if you stay within that delta, you'll end up lower than the level of smallness that you chose. One-sided limits are defined in their corresponding obvious ways. We adjust the limit as x goes to a from the right by choosing 0 is less than x minus a is less than delta without the absolute values. And the limit as x goes to a from the left by choosing the other direction. X minus a is less than 0, but greater than minus delta. Even so, it's all based upon that basic principle. A 1 over tiny is huge. So, for example, if we have f of x equals 1 over x minus 1, this is just a horizontal translation of 1 over x. If we take the limit as x goes to 1 from the right, we will get plus infinity. If you plug in numbers that are just a tad above 1, 1 plus tiny, and subtract 1, you'll get 1 over tiny. That's huge. And if you take the limit as x goes to 1 from the left, you're taking numbers and plugging them in that are just 1 minus a little tiny bit. 1 minus tiny minus 1 is just negative tiny. 1 over negative tiny is negative huge. And the graph of this function looks like this. At 1, that's the dividing line, it goes up to infinity on the right, down to minus infinity on the left. And as x gets huge, the whole thing gets driven to 0 in both directions. As a simple variant, let's consider 1 over the quantity x minus 1 squared. This function can't put out negative values, it must be non-negative values only. So at 1, yes, you'll get blow up, but in the positive direction on both sides. You can see then that the limit as x goes to 1 of 1 over the quantity x minus 1 squared is positive infinity. As you can see on the last couple examples, we have what is called a vertical asymptote, but we have not technically defined what we mean by vertical asymptote. And this class gives you the first opportunity to formally make that definition. Definition. A function f has a vertical asymptote at x equals a if either 1, the limit as x goes to a from the right of f of x is plus or minus infinity, or 2, the limit as x goes to a from the left of f of x is plus or minus infinity. In other words, at x equals a, we're allowing the function to blow up to plus or minus infinity on one side, but on the other side the limit can exist, or even the function value at a might be defined, and that's perfectly okay. All we require for having a vertical asymptote at x equals a is that the function blow up on the right or on the left, not necessarily both. Where do you go hunting for these vertical asymptotes? Well, the next theorem tells us that for rational functions, you look for roots of the denominator, provided they're not also roots of the numerator. So, as an example, if I have the rational function, what does rational function mean? Does it mean talks and makes sense? No. Rational means a ratio of polynomials. A function that is a ratio of polynomials is called rational. Consider x minus 1, x plus 2, x minus 3, x plus 5. In this case, if I plug in numbers that are close to 3 but not quite 3, say 3 plus a little tiny bit. 3 plus tiny minus 3 is tiny. That puts a tiny number in the denominator. The numerator is not going to be tiny. If I plug in 3 plus tiny here into this first factor, I get 3 plus tiny minus 1 is 2 plus tiny, close to 2. And in the second factor, it'll be close to 5. And if over here in the denominator, 3 plus tiny plus 5 is close to 8. This is the only factor that becomes tiny. The rest of it just becomes some real number that is finite. So we get a finite number divided by a tiny number in the denominator. That makes the whole thing blow up. So we get a vertical asymptote at x equals 3. You can see it right here. And over on this other factor, the vertical asymptote comes at x equals minus 5. If f of x equals p of x over d of x, where p and d are polynomials, i.e. f is rational, it's a rational function, and if p of a is not 0, but d of a equals 0, so a is a root of the denominator, then f has a vertical asymptote at x equals a. It tells us you go hunting for those vertical asymptotes, with respect to rational functions at least, in the roots of the denominator. So for example, suppose that f of x is x plus 7, x minus 5 over x plus 3, x minus 2. Find the vertical asymptotes. The solution is trivial. X equals minus 3 and x equals 2. These are equations for vertical lines. In our next example, we're going to look at certain limits. Suppose the limit is x goes to 1 from the right. We're also going to do the limit as x goes to 1 from the left. Let's look at x squared minus 4x over x minus 1 and x squared minus 4x over x minus 1. We'll see what happens as we go to 1 from each side. As we go to 1 from the right, we're plugging in numbers just a tiny bit bigger than 1. 1 plus tiny. That makes the denominator a positive but tiny number. In the numerator, keep in mind that x is getting close to 1. 1 squared, or anything close to 1 squared, is still going to be close to 1. Minus something close to 4, this is going to be negative. So I get something close to negative 3 divided by positive tiny. As you can see, this limit must be minus infinity, not plus infinity, because the numerator was negative. Negative over positive is negative, but tiny in the denominator, huge. Therefore, we go to negative huge or minus infinity. Let's suppose that we're going to 1 from the left. We have numbers 1 minus a tiny little smidge. 1 minus tiny minus 1 gives me a negative tiny number here in the denominator. But we're still close to 1. So we're still close to minus 3 in the numerator. Negative 3 over negative tiny, negative over negative, is positive. But with a tiny number in the denominator, it's positive huge. So this thing blows up to plus infinity. The next theorem gives us some rules about these infinite limits. We're going to suppose that the limit as x goes to a of f of x equals plus infinity, and the limit as x goes to a of g of x is some limiting value L. Then what happens in the limit as x goes to a of f of x plus g of x? Well, g is going to L, but f is going to infinity. Infinity plus L, well, that's just plus infinity. The plus L doesn't matter if the other one's going to infinity. What happens in the limit as x goes to a of f of x minus g of x? Well, again, the minus L won't matter if the first term is going to infinity. The infinity term kind of dominates everything. What if we're not adding or subtracting? We still have multiplication and division to work with. If we have f of x times g of x, the limit now depends upon whether or not L is positive or negative. It goes to plus infinity if L is positive, and it goes to minus infinity if L is negative. But in mathematics, there's a principle called trichotomy. That says every number is either positive, negative, or 0. What if L is equal to 0? If L is equal to 0, that's an indeterminate case. You can get different values depending upon how f goes to infinity and how g goes to 0. We'll talk about those indeterminate cases later. This theorem has two more cases. In case 4, what happens in the limit as x goes to a of f of x over g of x? And again, the answer will depend upon whether or not g is positive or negative. It'll go to plus infinity if L is positive, and minus infinity if L is negative. If L equals 0, there's a bit of a question mark. The last case, what happens if the finite limit occurs on the top? If you're going to only a finite value on the top, positive or negative, if the bottom is blowing up huge, 1 over huge is tiny. The whole thing gets driven to 0. I want to look at an example. As you know, the tangent function looks like this, and it goes through the origin at a 45-degree angle. But as you go to pi over 2 from the left, the tangent function blows up to plus infinity. And of course, as you go to pi over 2 from the right, it goes down to minus infinity. Let's consider the following example. Let's take the limit as x goes to pi over 2 from the left. The top is just going to be x squared plus 1. The bottom, the tangent of x. Now the top goes to pi squared over 4 plus 1. That's a finite positive number L. The bottom is going to plus infinity, since we're going to pi over 2 from the left. Some finite number divided by plus infinity, the whole thing gets driven to 0. What if I have the limit as x goes to 0 from the right of the cosine of x times the natural log of x? You know that as cosine is sent to 0, cosine looks like this. As you go to 0, it goes to 1 from both sides. Log, on the other hand, goes to minus infinity. So log is going to minus infinity and cosine is going to 1. The whole thing goes to minus infinity. So we've seen functions blow up to plus infinity or to minus infinity. But what happens as x tends to infinity? How do we even define such a notion? Suppose we have some number L, and the function gets closer and closer to L as x goes to bigger and bigger values. We're kind of thinking the limit as x goes to infinity of f of x equals that limiting value L. It settles down on that number. How do we properly define that? By the limit as x tends to infinity of f of x equals L, we mean given epsilon greater than 0, we'll choose some measure of closeness in the range. There exists some n. If you go far enough out, function values will stay close to L. R positive is the set of positive real numbers such that if x is greater than or equal to n, then the difference between the function value and the limiting value will be smaller than the epsilon that you chose. Yeah, if you go far out enough, if x is big enough, then the function value and the limiting value will be close. So let's look at an example of how this works out. Suppose we have the function, say, 4x squared over x squared plus 1. The denominator does not factor over the real numbers, so this function does not have any vertical asymptotes. If you think about it, when you square a real number, you get something that's non-negative, positive or 0. Plus 1, the denominator is always at least 1. It can't get down to 0. There are no vertical asymptotes for this function. But what happens when x gets big? In the limit as x goes to infinity. Think of it as follows. If I plug in a big number, like, say, 1,000, what is 1,000 squared? 1,000 squared is 1 million. So the numerator is pretty close to 4 million. The denominator, we have 1,000 squared plus 1. That's 1 million plus 1. The plus 1 doesn't really affect the fraction very much. It's almost like you can ignore it. If you have $1 million and $1 falls out of your pocket, do you really care? You still have 999,999 to worry about. So, as x gets big, we're getting something close to, when x is, say, 1,000, 4 million over 1 million-ish. 4 million over 1 million-ish is about 4, which means the plus 1 really doesn't matter. As x gets big, if the bigger the number you plug in here, you plug in 1 million. 1 million squared is 1 trillion. 4 trillion divided by 1 trillion-ish is really, really close to 4. So you can see that as x goes to infinity for the function 4x squared over x squared plus 1, the function values tend towards 4. Aha! What if the limit was like this? The limit as x goes to infinity of 4x over x squared plus 1. Let's try this one out with large values of x. If we plug in something like 1 million, the numerator is 4 million, but the denominator is close to 1 trillion. 1 million squared is 1 trillion. 4 million divided by 1 trillion-ish is very, very close to 4 divided by 1 million, which is a very tiny number. the bottom is blowing up faster than the top because the bottom has higher degree. The higher degree polynomial wins the race to infinity. The limit is 0. The bottom blows up faster in the race to infinity, so that drives the whole thing down to 0. And finally, suppose we're taking the limit as x goes to infinity of 4x cubed over x squared plus 1. If we plug in x equals 1,000, the bottom is still just a smidge above 1 million. But what is 1,000 cubed? 1,000 cubed is 1 billion, so the numerator is 4 billion, and we're divided by 1 million-ish. This fraction is very, very close to 4,000 when x is equal to 1,000. I think you can see that as x goes big, the numerator wins the race to infinity this time, and you end up with positive infinity. There are some little technical details we need to pay attention to. Suppose x is going to positive infinity, and we're looking at negative 4x cubed over positive x squared plus 1. Now you have a positive number cubed is positive, but it's multiplied by a negative 4. The numerator is negative. The bottom is always positive on this case. The thing gets driven to minus infinity. What if I had the limit as x goes to infinity, positive infinity, of negative 4x cubed divided by negative x squared plus 1? Now the numerator and denominator are going to be negative when x gets huge. We'll have a negative huge over negative not quite as huge, but still huge. The top wins, negative over negative. The limit is positive infinity in this case. So what's the moral of this story? The higher degree polynomial wins the race to infinity, but you need to pay heed to the coefficients. And in particular, the leading coefficients of both the numerator and the denominator when evaluating these limits. We have the following theorem. If f of x equals a rational function, we'll have the numerator be the polynomial p of x and the denominator be the polynomial d of x, where p and d are polynomials. Then there are all these cases. The limit as x goes to plus or minus infinity of p of x over d of x will be 0 if the degree of d is strictly bigger than the degree of p. So if the denominator has larger degree, then it blows up to infinity faster than the numerator, and having big numbers in the denominator drives the whole fraction down to 0. 2. If the degree of d equals the degree of p, then the limit as x goes to plus or minus infinity of p of x over d of x is the ratio of the leading coefficients. So for example, if I have the limit as x goes to, let's say, minus infinity of 4 x cubed plus 7x minus 9 divided by negative 5x cubed plus 2x squared plus 7x. The leading coefficients are the coefficients of the highest degree terms. Nothing else matters. If I plug in x equals 1,000, 1,000 cubed is 1 billion. The first term is 4 billion-ish plus 7,000. If I have $4 billion, do I care about 7,000? I could spend $1,000 a day, every day, for the next 1 million days, longer than the rest of my life, and still have money left over. So this term, the leading term, is the one that matters. The rest, they don't even matter. Just forget about them. Cover them up. In the denominator, again, the only term that matters is the one with the highest power. The others are going to be so small when x gets big that you can ignore them. The answer is 4 over negative 5, because the powers are the same. But by trichotomy, there is one more case. Third, if the degree on the top is larger, then in the limit, as x goes to plus or minus infinity, p of x over d of x will give you plus or minus infinity, one or the other. I'm actually concealing a large number of little subcases as to whether or not you get plus infinity or minus infinity. You have to be careful in analyzing whether or not you're going to plus or minus infinity, whether the leading coefficients are positive or negative, and whether those powers of those leading terms are even or odd. It all makes a difference in whether or not you get plus or minus infinity. Let's look at an example. Let's suppose we're taking the limit as x goes to minus infinity, and let's have 3x cubed plus 1 over negative 4x plus 2. We need to be very careful in this analysis. We're plugging in negative huge numbers, and negative huge cubed is still negative and even more huge. Times 3, negative huge. The top is bigger. The top is going to win the race to infinity. That doesn't mean we get to ignore what happens in the denominator. X is going to be negative and huge. Times another negative gives you a positive. So we have negative really huge divided by positive big. That gives us negative infinity as the limit. If we change this example just a little bit, it changes the outcome. Let's make the denominator have a degree of 2 now by giving a negative 4x squared plus 2. X is going to minus infinity. The top is still going to be negative huge. In the bottom, we have negative huge squared, which is now positive and huge. Times a negative gives us a negative. We have negative divided by negative, but the top wins the race to infinity. So, in this case, the limit is positive infinity. Notice we had to take into account whether or not these powers are even or odd, and whether or not these leading coefficients are positive or negative. All of that has to go into our analysis. Let's look at the limit as x goes to positive infinity of e to the x, and the limit as x goes to minus infinity of e to the x. Now for rational functions, if you get a finite limit, you'll get the same limit whether it's to plus infinity or minus infinity. That's not true for e to the x. The function e to the x goes to plus infinity as you head out to infinity on the right, and as you head out to minus infinity on the left, the function goes to 0. Let's look at the limit as x goes to infinity of x squared over e to the x. What we're doing is we're pitting one function that blows up to infinity versus another. And the value that you get will depend upon which one blows up to infinity faster. Well, exponential functions grow faster than any polynomial on the way to infinity. The denominator blows up faster, the whole thing goes to 0. You could also ask, what happens as x goes to minus infinity? Both of these functions are positive, but e to the x goes to 0 as you go to minus infinity. So you get positive huge divided by positive and yet tiny. 1 over tiny is huge. The whole thing goes to plus infinity. Let's do some hasty examples. The limit as x goes to infinity of 3x over 4x squared plus 9. You can see that the degree in the denominator is greater than the degree in the numerator, so the whole thing goes to 0. If we take the limit as x goes to infinity of 3x squared over 4x squared plus 9, now the degrees are the same, so you take the ratio of the leading coefficients as your answer. And the limit as x goes to infinity of 3x cubed over 4x squared plus 9. Now, the top blows up faster. Everybody's positive as we're going out to positive infinity, so the limit will be positive infinity. You might equally ask what happens in the limit as x goes to minus infinity of 3x cubed over 4x squared plus 9. The bottom stays positive. The top wins the race to infinity, but a negative huge number is still negative. Times 3, still negative. This whole thing goes to minus infinity. So what is a horizontal asymptote? If the function tends towards some finite limit L, then y equals L is a horizontal asymptote. Keep in mind, you could have some other value that you tend towards on the left. Who knows what it tends to in between? But if it tends towards a different limit on the left, there's two directions you can go. There's right and left. You don't have to get the same limit if you go to plus infinity or minus infinity. For rational functions, you always will. There will be at most one horizontal asymptote for rational functions. But there are significant examples where you get two distinct horizontal asymptotes. And if you think about it, you can't get more than two. If you had a third, well, it wouldn't be a function anymore. The line y equals a is a horizontal asymptote of the function f if either 1, the limit as x goes to infinity of f of x equals a, or 2, the limit as x goes to minus infinity of f of x equals a. It has to go to a either as x goes to infinity on the right or on the left, or both. This or is the mathematical or. This or that or both. So for example, let's look at f of x equals arctan of x. Now, this particular function is kind of special. Draw in the tangent function sideways. That gives you the inverse tangent. In the limit as x goes to infinity of inverse tangent of x, the function tends towards the value pi over 2, and in the limit as x goes to minus infinity, the function goes to minus pi over 2. It follows that we have two horizontal asymptotes, y equals pi over 2 and y equals minus pi over 2. I want you to remember this example. Let's look at f of x equals sine of x divided by x. As you can see, sine stays bounded between 1 and negative 1. So sine of x over x stays bounded between negative 1 over x and positive 1 over x. Well, technically, if x is positive. If x is negative, you have to reverse the direction of the inequalities. But you'll still get the same sorts of bounds. And we will have a squeeze theorem. In the limit as x goes to either plus or minus infinity of plus or minus 1 over x. Since the bottom blows up, the whole thing gets driven to 0. That implies by the squeeze theorem in the limit as x goes to either plus or minus infinity, sine x over x gives you 0. You can see the principle here being that the bottom blows up, but the top stays bounded. When that happens, the whole thing gets driven to 0. I want you to remember these two examples. The limit as x goes to 0, sine x over x is 1. We spent a long time proving that. That's hard won. You need to remember that. But in the limit as x goes to infinity, sine x over x, you get 0. That too is important, and you're likely to see both of those on the next exam. The reason is, I want you to pay meticulous attention to the details. You need to pay attention. Are you going to 0 or infinity? And not be like a fish that's pattern feeding. Ooh, this looks the same as that, so I'm just going to eat it. You end up being snagged with some bait on a hook, and you end up on some frying pan. Don't let that be you. Make careful distinctions about this or that. What happens in the limit as x goes to infinity of just sine x? Well, sine x doesn't blow up, but it doesn't settle down on anything either. It's bounded, but it doesn't tend towards one particular value. It just keeps oscillating up and down. So this limit just does not exist. On the next example, we'll find the horizontal asymptotes of the function f of x equals e to the x plus 1 over e to the x minus 1. To determine the horizontal asymptotes, we have to take the limit as x goes to plus infinity and also the limit as x goes to minus infinity of the function. As x goes to plus infinity, these plus 1s won't matter. The e to the x terms blow up. They go to infinity, and at the same rate, top and bottom. So the limit will be 1. In the limit as x goes to minus infinity, e to the minus infinity, well, e to the x goes to 0 as x goes to minus infinity. So the e to the x in both numerator and denominator will go to 0, leaving 1 divided by negative 1. So this function has two distinct horizontal asymptotes. As you go to the right, it tends to 1. As you go to the left, it tends to negative 1. When x is equal to 0, you get e to the 0 is 1 plus 1 is 2. And in the denominator, you have something that goes to 0. E to the 0 is 1. 1 minus 1 is 0. You will, in fact, have a vertical asymptote at 0 as well. So what does this function actually look like? If you're to the right of 0, e to the small positive number is a number that's slightly bigger than 1. We get positive and tiny. The numerator is always positive. The thing must go to plus infinity as you go to 0 from the right. What happens as you go to 0 from the left? E to the x will be slightly less than 1 if x is left of 0. And so you'll end up with negative tiny numbers. The function will go to minus infinity on the other side. So we have y equals 1 and y equals negative 1 as our horizontal asymptotes. There's also a vertical asymptote at x equals 0. Let's do some more hasty examples. The limit as x goes to infinity of, let's say, 3x plus 2 over 5x plus 7. What is the limit? Degree is the same, top and bottom. The limit is 3/5. What's the limit as x goes to infinity of 4x squared minus 7x cubed over 5x squared plus 2x minus 1? Now, this minus 7x cubed is the leading term, whereas the leading term in the denominator is this 5x squared. The top is going to win the race to infinity. The question is, do you get plus or minus infinity? The answer is minus infinity because of this negative. Now, this was purposefully misarranged in the top and not placed in the usual descending order in order to force you to look carefully at what was the highest degree term in the numerator. I'm probably going to do something similar to you on the exam.